Hi, so today's tutorial, we are going to study about static stress analysis. We are going to study how FEA can be used to study a material which is subjected under a condition. So static stress analysis is something that we use to study a material if it can fail or it cannot, depending on what you want to use the material for. So before we start, let's do a quick recap on static stress. Okay, so static, static stress, it doesn't depend on time. That means there's no time dependent. When we subject the body under a certain force, we are just looking for a result at a particular time, not within a period of time. You understand? So that is the whole thing about static stress analysis. So it doesn't depend on time. And also, it depends on the material properties. So in static stress, the material property is what determines the strength of the material. You understand? So it's basically the stress and strain. We just want to know whatever we are going to use the material for, is it going to withstand, or is it best for is it best for us to use that material for that particular condition or not? So basically, that is how static stress also works. So if you compare aluminium to copper, you all know that the material properties of aluminium is different from copper. If you compare aluminium to cast iron, you know that material properties of aluminium is different from cast iron. And we all know that at least cast iron is more stronger than aluminium. So if you subject these two different material under a certain force, both of them, one will die, like one will deform completely. You understand? So they all have a purpose and what you can use for. You understand? So that is basically what static stress analysis deals with. So when talk about stress, stress is simply force over what area. And force is what? Newton, and then the area is what? Millimeter square. Remember, we can change it. It depends on the unit they are using for the area. If the unit is centimeter, it will be centimeter what? Square. If it is meter, it will be Newton meter square. And also, Young modulus. Young modulus is stress over strain, which is stress is force over area, and then the strain is what? The original length over change in length. Typically, it is it is change in length over original length. But because when you divide it, it will change. So that is why it has become length over the original length over change in length. Okay, so when we replace it with the unit, which is the Newton over millimeter square, which is the millimeter times the millimeter over millimeter, they cancel out and we get this as the unit. You understand? So typically that is what it is. Now, this is the question that we are checking. So an axial pull of 35,000 Newton is acting on a bar consisting of what? Three lengths, as shown in figure 1.6, which is section 1, section 2, section 3. So section 1 has 20 centimeters with diameter of 2 cm, and then section 2 has diameter of 3 cm, and then a length of what? 25 cm. Section 3 has diameter of 5 cm, and then length of what? 22 cm. And it is an axial pull. So the axial pull is like if you look at the pull, it is opposite direction to each other, which is tensile strength. So it's axial, which means the force or the tensile pull is acting on the axles of the bar, which is the center of the diameter of the three diameters. You understand? That is why you can see it exactly at the center. So, and he said if the Young modulus is 2.1 times 10 to the power 5 Newton per millimeter square, determine the stresses in each section and the total extension of the bar. So you realize that they want the stresses in each each section, and then the total extension, the deformation, you understand, yes, of the bar. So that is why I quickly grants you through the young modulus and then the stress and the important things. So because it's a bar, we are not using, the area will be pi d square over what? 4. Pi d square over 4. You understand? Because it's a bar, the area will be pi d square over 4. The concept about this tutorial is not about using hand calculation, but however, you can use, with what I've just shown you, you can use it to do the hand calculation to get the answers. But here, our focus is to use the FEA, which is the finite element analysis, to what? Do the testing. You understand? So why are we using that? If you compare to the olden days, back in the olden days, when a scientist or an engineer wants to do a test like this, they have to go to a lab where they have devices. You have to get your material that you want to do, the material, let me say cast iron, for instance. You get a cast iron, then you go, you subject it, you put it under a load of what? 35,000 Newton. Then you put it, okay, so you put it on it, you act the force of the 35,000 Newton to it to see whether the material can withstand what you want to use it for. You understand? So that is typically what the olden days they do. Why are we using it again? It requires time. If in the olden days, when they go to the lab and do all these things, it takes time, material, resources, and all these things. You understand? They have to go, and if you are using aluminum to do something that you want to test, you need to get the actual aluminum and then act it. And when you are done, it becomes waste. You understand? Yeah, so waste of resources, time, and then other, what do you call it, equipment as well. But however, this is the new era of transformation, like I always tell you in design engineering. So in this new era, this whole lab that in the olden days they go, we have this whole lab digitally. It has been designed in a digital form. So without much ado, this we are going to use Autodesk Inventor 2026. That's what I use to design the material or the bar and then test it without using physical equipment, like I told you. And trust me, if you do the hand calculation, it's supposed to match. Even if it doesn't match, there will be like 1 or 2 variations, okay? So you do it, it has to be close to the answer. And trust me, if you get the values, if you go and test the thing in real world, you are going to get the same values if you have your instrument to measure the values after you do the physical testing. It's going to give it to you. So this FEA help us so that we don't waste much time. We can do everything within the shortest possible of time and get our result to fast forward our design process. You understand? Yes. So that is typically the concept of FEA analysis. So I'll come to new. I'll come to new. Let's start new quickly. So let me check my unit. Okay, so it's already in millimeter. So I can start quickly. I'll choose this XY plane. So the first section is what? Diameter 2 cm with a length of what? 20 cm. So a simple circle, 2 cm, then finish sketch, extrude with 20 cm. Okay, so this is the first bar. Then I will come to the second bar. Which is, what's the second bar? The second bar is 3 cm with the length of, or diameter is 3 cm and the length is 25 cm. So 3 cm, enter. Then the length is 25 cm. So quickly, let me finish the third one. Okay, so we are done with the bar. We have, you can see here, I have my section 1, which is this one, which is 20 cm with the diameter of, sorry. So we have the bar, which is 20 cm. The section 2 is what, 25 cm. And then section 3 is also what, 22 cm. You understand? Yes, with 5 cm. So you can see it clearly here. 5 cm, 3 cm, and all these things. So that is just the bar. So now we are done with the bar. So what we need to do is to apply the material. Like I told you, it depends on the material. That is going to tell you whether the results of the stress you are going to subject into it. All right, so we have material properties that we can do. So before we apply the material, we will move to stress analysis, which is here, you see, stress analysis. So I'll come to stress analysis. Then I'll come to what? Create steady. So when you go to create steady, you static analysis. You see, static, because static analysis, stress analysis has no time dependent. It's under a constant time. So I come here. So this is the lab. In the olden days, the lab they have, this is the lab of the digital version of the lab in when you want to do static stress analysis. You understand? So I don't need to buy any material. I don't need to go and look for it. Everything is digitally here. And it is the same as what you would do in real world. Yes. So this is the practical thing we are doing. All right. So I will assign the material because technically what we have done here doesn't have any material. So it's kind of an object, nothing. You understand? It has no properties, nothing. So I'll come to assign material. Then I will choose material. So I'll come to material and then let's see. I will choose, let me say maybe steel cast or something like that. Okay, so steel cast. However, in the question, they didn't indicate steel cast or cast iron or something. They said it's acting on a bar consisting of 3 lanes. So they gave you the bar, but the properties of the bar is what? The Young modulus. So the Young modulus is part of the material properties we are talking about. You understand? So when you deal with stress and strain analysis, you come across all these Young modulus, elasticity, and the rest. So that is just that. Okay, so let's begin. Let's apply, let's go and create our own material property that has this Young modulus so that it can give us the result we are looking for. Remember, if the material does not have this property, when you subject it, it will give you different things. Like I told you, if you subject aluminium with as compared to cast iron, the two of them are not going to give you the same result. So get to know that because of the material property. So let's apply our own material property. So I'll come to material property here, materials, then choose. You can choose any material, but I will choose steel cast. All these material that is listed here are standard. Okay, they are standard. That means it's international. That is American standard, ASME, American standard of something, some society engineering. So they have standard properties that cut across the world. But however, this is our own design problem. So we need to change it. So before we can change it, we need to copy it. Okay, we need to duplicate to make it our own. So I'll call it cast iron copy so that we can get access to change the physical properties, the properties of the material. So we come to the properties. Under the properties, we have, you come to physical. So we have basic thermal, mechanical, and strength. So if you are dealing with thermal energy, which is heat and all these things, the properties of, the parameters of when you deal with thermal energy or heat related stuffs, you can have the things here, which is specific heat of the material, the thermal, all these things are listed to define the material. Remember back in basic mechanics, the material properties of, these are the things that define the material, whether it will be suitable for whatever you are using it to do, okay? So ours will, because we are doing with static, ours will fall under mechanical. So under mechanical, we have the Young modulus. So in American standard or the standard iOS, the standard of the cast iron is what? This is the Young modulus of it. But with respect to our question, it is stated in this way. So we have to design our own bar with a certain property. You understand? So now it is what? 2.1 times 10 to the power 5. So I'll come here. So 2.1 times 10. So the E stands for the exponent. Okay, so times 10 plus 0.5. So that is the meaning. So we come here, we go to what? Apply. Okay, so we have applied the property to this cast iron copy. You can see it here. So I'll come to this. You can see it. Let me go to physical, mechanical. You see that 2.1 E plus 0.5. That means 2.1 times 10 to the power 5. Okay, so now we apply it to this, to our material. So we go to, this is our design. We come to assign material. So these are the process for you to do. So we, in other words, we are setting condition to our object. Okay, so let me apply the material. We are defining the type of material of our object we are going to use for the test. So I'll come to here. So material override. I'll come here and I'll choose the steel cast copy. Yeah. So you can see it here. It has been part of the list. So this is the standard and this is our edited one. So this is it. And I'll choose OK. So it has been override with this property. So you can see that the material have even changed. The appearance have even changed clearly. Yeah. So that is just. Then we will come to constraints. So constraints is more like limiting the degrees of freedom. Okay. Let me give you real world example. If you are going to do hydraulic press of an object, maybe you want to insert a bar into a bearing, you need to, you have to let something hold the thing for you before you can do the hydraulic press. You understand? So if you, maybe you can use a vise or something. So if you let, you using the vise to hold the material is, in other words, it's a constraint. You have limited the movement of the objects you are dealing with so that you can apply the forces. If you want to, let's say you want to do cutting, you want to cut a bar, you hold it, the bar, or you want to cut a square pipe, you have to put the square pipe inside the vise for the vise to hold it firmly for you. So the vise holding the thing firmly, it has cancelled or it has limited all the degrees of freedom. So that when you cut, when you are cutting and you are applying the force in cutting, the bar will not, the square pipe will not be burning. You understand? So in other words, we want something to hold. So all these are method of what? Applying constraints to it. So in other words, we want a fixed constraint. That means we want it to be fixed. Okay, good. Now, in our question, because the forces are tensile, you understand, they are stretching on opposite side, we have to let the fix, we have to hold it somewhere in the middle. Okay, so the fixed constraint, I will hold it here, this portion. So something is holding it here. Okay, all right, so it is fixed. Now it is fixed. Okay, yes. So what next? We are applying condition to the material. Now we have defined our material of the bar. Now what we have to do is to apply the force. Where is the forces being applied? Now, before I apply the force, I need you to understand this. Because this is digital, this bar that we drew, we just use the drawing sketches to draw. It is hanging in air. And when the thing is hanging in air, in engineering, when something is hanging in air, we use X and Y to determine its position, like I told you before. We use X and Y to determine its position or the magnitude, everything. X and Y, Z, because it's 3D, it is X and Y, Z to determine its position. So that is why I can rotate it. You don't know where it is, whether it is on the ground. It is not on the ground. So for us to determine its position, it is the X and Y axis. That is why you can see here the X, Y, and Z. And you can see that the bar is totally in line with the what? The Z. So let me show you. So you can see that it's in line with the Z. You see? So it is in the axial, or it is in parallel with the Z axis, okay? Yes, and then the Y is rather the vertical side, and then the X is the opposite. Now you understand? So this is it. So we can determine the position of it. So when we are applying the force, we need to know the axles. So the bar is on Z axis. Typically, the center of the diameter of the bar, you understand, the center of the bar is on what? On Z axis. That is why it's in the same direction. So when we are come to apply our force, first, the force stated in the question is what? 35,000 Newton. So I'll write it here, 35,000 Newton. So I'll choose my location, which is this side. Remember the position is opposite, okay? So you can come to magnitude. So you can see that force at X, which is in this direction, is what? 0. Force at Y, which is the vertical side, is also what? 0. And force at Z is what? 35,000, because I place it axially to the Z axis. So the question is axial what? The axial pull of 35,000 Newton. So it is now axial. So the axial is what? Is parallel to what? It's in Z axis. So that is why it's supposed to be in this way. So if I want to apply the force on Y axis, I'll just have to delete this one and then put it here. You understand? Yes. So understand. And I believe you have understood what I'm saying. Now, the forces are in both sides. So I'll apply another one. And that will be opposite, and it is what? 35,000 N. Okay. So now you can see clearly that we have set our bar into the let me say the machine that is going to do the tensile stress for us, the tensile pull for us. Okay. Yes. So now we have done that. We can also apply gravity, because remember that any object also acts under the influence of what? Gravity. So we can apply gravity. So in order to apply gravity, look at the axles. Well, so the vertical side is what? The Y. You can. Why not? So maybe I'll come to Y. So let me say I'll apply it. Let me apply it. So apply it here. Let me say here. No, it shouldn't be in this direction. It's supposed to be vertical, like I told you. So the vertical is what? Y. So I'll come to vector component. So it's Y, okay? So because it is using millimeters, that is why it is on 9.8. So 9.8 will be meter per second square, but it is millimeters. So 9,800 and what? 10.0. Enter. Then I will change, sorry, because it's 2, that is why it has become this way. So let me come to load and edit the gravity. Then I will change this one to 0. Enter. So you see that it has rather go downward. It is pointing upward. Gravity is always pointing downward. So I'll come back again and edit it and then bring maybe negative to it. Yes. So now we see. Yes. So this, remember, this this is a recap of the simulation concept we hosted. Because of the network and people didn't really attend, I am doing this thing so that you can also have time to understand it better. Okay. Yeah. So since now I've applied my gravity, we are good to go. Now we can do meshing. Meshing is another thing. It's basic mathematics in the GHS thing, but it will be another another tutorial. So we apply, let's do the meshing. So this is the meshing. Now let's do the simulation. Let's apply the simulation. Let's see what will happen. So we are done with our simulation. This is what's after the tensor pull. This is what happened to the bar. So let's compare our answers before I will do any other explanation. So this is the color variation tells you what is happening in the molecular structure, okay, the molecular structure, the atomic particle, what is happening. So that means if the stress is time dependent, over time, here is what is going to fail first. Here might get broken somewhere. That's why here is red. So the more the red, that is where the maximum force was done. And it actually makes sense, yes, because why here is more red? Because the diameter here is the smallest one as compared to the second section and then the third section. Because the pull is on both sides, 35,000 Newton on both sides. But here is more red because the diameter is small. Okay, the diameter is very small. So if there is any fracture to happen, it has to happen here. That is why you can even see at this particular point that at this particular step, that this is where the reddish zone is more. So that means this is what is actually going to happen over there. But before I do a further explanation, let's check the values, okay? So I'll come to probe 0.1, 0.2, and then 0.3. So I'll move this section 1, section 2, and section 3. If you don't get it 100%, it's more closer, okay? So get to know that. So at section 1, we have 111.48. Here we have what 116. Yeah, that is a bit, there's small gap at 5 difference, but it's as close. Okay, that is not the main thing, but it's your answers depend on the conditions you set. So you need to iterate your design. This is the benefit of digital FEA. Okay, you see when we did do this after this first test, this is what we had. No, it's too far. We need to do another test. We need to iterate. So we go for another material. We maybe increase the diameter or a bit. Let's go and do another test. Let's see if we can get the result we are looking for per our calculation. At the end of the day, after you do all this iteration in a lab, you are going to waste a lot of material. But right in front of here in the digital lab, you can just do anything, just test it. This is the lab of it. This is why practically we are moving so that we can speed up our design. You understand? Yes. So this is 116. The middle one is what? 52.3 megapascal. So let's check the middle section. The section 2 is what? 49. So there was a bit, I think 3 difference. And then the last one was what? 17.9 megapascal. Let's see that one too. So the last one is more close to. It was 17.825. And we have 17.89. So this is it. So we can, maybe I didn't do something correct. Maybe I have to, let me take off the, what do you call the gravity, or let me go and change some material property over there. Maybe that is what caused the influence of the results so that we can get as close to it. You understand? So all these things are there. So it's good we even got this. Look at, I did my first test, and after we did the first test, this is what I had. Let me show you. So you see that my first test, I got the first section, I had 111.5. So we go to the answers. I have 111.4. The second section is what? 49.6. The second section is what? Um, 49.5. So you see, and then the third one is what? 17.8. And look at mine, is what? 17.8 exactly. So this is it. You see, so look at even this one. The red zone is actually close to what? The bar. You understand? So that means if it is to get fractured, if it's to enter into the what do you call it? The 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 fracture, is it plastic and this thing deformation chart? For you to enter into the plasticity mode and then get break off finally, it has to. So all these things, this is where it will break off. This is the first point it will break off. And in actual sense, like, it actually makes sense because here is the smallest diameter. So the smaller the diameter, the higher it will get bent over time. So this is the distance of what happened. So this is the original length. You see, so bar one, this is the original length of what we designed. And this is the final after a certain time. I told you it doesn't depend on time. However, we want to see the process. How did it got there? Why not? We have the software for us, so I can come to animate under 10 seconds. Let's see what will happen. So you see, when we are applying under 10 seconds, this is the original material. And this is where under 10 seconds, after the pull, this is where the stretch, it was able to elongate. The length changes. So you see, this is where it got to. So after exactly on 10 seconds, this is what we had. Remember, it's a time, it doesn't, it's time, like, it doesn't depend on time. So if you want to do a time dependence, we have that one. So I think it's dynamic simulation. We call it dynamic static something. So you give a time to it and then you apply. So in our future simulation tutorials, we are going to discover all and we are going to understand. So stick with us, follow us, and then you will understand more. Try other things, tweak it, iterate, just test it. If you have any doubts, just try. This is why you have it digitally. You have the opportunity. So try. If you have any question, anything, just put it down in the comment section. I'll review them, I'll answer. If you also try anything and you don't understand along the line, bring it on board in our comment section, and then I'll come in. We will even use it in our next tutorial. Okay? Yeah, so this is where I will end the tutorial. And I thank you all for this. Have a great time.